Okay, let's set up the environment as it's supposed to be. It's supposed to be like this. Now let's my throat is a little bit bad, so I apologize for that. I'll just clear out here. Mendo.mk. I hope we are okay with the stream. I know I don't have a thumbnail. It's my first stream, so we'll fix that later. Okay, so I'm going to try to solve some algorithms. Now, I don't know if they're going to be really hard or really good, but well, it's what we can do. Well, Erenka, I know it's a dynamic programming problem. I already know the solution to it. Maybe we start with something like simpler, even though this I have like sent some code. This was this problem. I will translate all of the problems. I'm just reading it right now. The solution. So this problem is a little bit like, I don't know, crazy. It has only 18% solve rate, but I know the solution to it. I just don't know if it's, I mean, it's greedy solution. I don't know if it's the right problem to start with. Maybe something like easier, and then we'll go on it. Maybe start with like one problem which I really like but I haven't solved, and this is this problem. Or was this problem? Yes, so it's this problem, yes. Okay, let me start. Let me read it once again, and then we'll let's see on YouTube how are we doing. Okay, let's see. Let's read the problem. Yes, okay. So yeah, this problem is actually based on ACM problem, but I don't know why it's like it shouldn't be so difficult. It's quite an easy one, and I have already explained this problem on one of my workshops. Let's see. So you're given. Okay, so yeah. So you're given some numbers, like an array of numbers. Let's take this. Let's take what array is good array. I know this is okay. This here. Okay. So you're given an array. Okay, I was just reading if I'm okay, if I'm correct. Yes. So with this array of numbers, what you need to find is you need to find the number. So find the number, maybe a little lighter pen. Find the number of triples such that, so a triple, let's define what is a triple first. A triple is, let's say, x, y, z, such that x is bigger or strictly bigger, or it's equal, can be equal as well. Yes, I think it's strictly bigger, and this is strictly bigger. Also, probably distinctive numbers. They're all distinct numbers. Yes, all are distinct numbers. So you need to find the number of triples such that x, y, and z is like a triple, and then each triple has the, so it's okay, it works. So each triple x is like bigger than y, and y is bigger. So one triple from here would be, let's say one example would be 190, 180, and let's say 168. So this is a valid triple, right? Also 190, also let's say 180, 170, 160. They don't have necessarily to be like, they can be like, you can have like here a number, and then there a number. So it doesn't necessarily have to be in the like continuous subsequence. It's not a continuous subsequence. So how do we solve this problem? If you like want to try it out, I don't know what to do. Like probably, I don't know. I want to tell you the solution to solve it. I don't have time to wait. But okay, so the solution is pretty simple. You have this array, and what you're looking for is, so let's say, how do we explain this? So for every triple, if I find like I'm here on 180, let's say, then I can easily look how many numbers are bigger than 180 on the left side and are smaller than 180 on the right side. Okay? So I can easily do that because I only need the number of numbers here and here. So let's say you have some numbers here, and then this is the number I'm currently at, and then you have some other numbers here. I'm drawing the numbers on like a graph more, so you can see it. So I'm interested here for this number, which numbers are bigger than that on the left side and smaller than it on the right side. So let's see, let's put here two numbers. So let's say these here are, so I know that on the right side of this number there are two numbers which are smaller, and on the left side, let's say there are three numbers which are bigger. So maybe this was like, this is on the right side, I want from like 180, I want here a smaller number. So I find two numbers which are smaller, and here there are three numbers which are bigger. So the total number of contributions that this number has, that 100, let's say the number that we are at has, is 3 times 2, because for each here number for each number on the left side, you can have two numbers. So I can match this, this, and this. I can also match this, this, and this. So it's very simple, self-explanatory mathematics. And then how do we find the number of numbers on the left side and the number of numbers on the right side? It's pretty easy if you know sets. What you can search for, so I want in logarithmic time, log of n time, say how many numbers are smaller on the right side than this number. So what you're gonna keep is two different sets. One set which is on the left and one set which is on the right. And you can query out this set on the right for like how many in log of n time, how many numbers are smaller than this. And similarly do for bigger numbers on the left side. So log of n to do that, and for n times, because for each number we have to do that. I will tell you in the code how it works, but this is the whole complexity. And like there's nothing much really here to discuss, except maybe like if we have like, I'll have like now what is Macedonian? How do you mean what is Macedonian? Because like the trick here is that like the problems are well-known problems. I mean, not well-known problems, but probably you have seen them, maybe. You have seen their techniques, but they're written in Macedonian, so there are some problems which are authored by Macedonian authors, but there like some problems are not. So this problem, I have seen it already on an ACM contest, so it's not, I mean, I've seen a variation of this problem, so probably some combination. So I just said because it's written in Macedonian, so it probably is going to be hard. Like you can maybe translate it to English if you want, but there's like really stories. So like it's a very like simple problem when you write it like this: find the number of triples such that x, y, z, x is bigger than y bigger than z. So just the number of triples. It's not a complex problem. I think it's a great starting problem. For now, I will just create here a new file. Let's call it. Well, the problem is, it says photography, so photography. And let's fastly code it. So the trick here, what I am doing, so there is this CPH judge which allows you to copy sample test cases and see if you are right. So like what they're giving you on the input must match what's the output. So for all these sample test cases, they must match. So very quickly, we just have like a vector of numbers. Let's just call them A, because why not? Okay, let's insert them in the vector. So it's just an array, it's nothing more. And then we are going to have two sets of what is like DP front and DP back. And in the DP front set, we are going to insert, I think there must be at least 3 numbers, okay? Yes. We're going to insert the first number, and this is a of 0, and in the DP in the back set we're going to insert every number starting from, so not 0, not 1, but 2. So like if you have this sequence, what we are doing here is, let's say you have this sequence 10, 20, 40, 30, well, it has to be bigger, 90, say this is 80, 50. Okay, so what we're doing is we're adding on one data structure, we're adding this 9, and the other data structure, this whole array here, this set. So in turn, when we look for this, like this number will be in the middle, so we're going to look for like on the right, on the left, and on the right, how many numbers are bigger than this number on the left, and how many numbers are smaller than this number on the right. So, and then when we move to the next number, what we're gonna do is we're just going to take off this 80 and insert it in the other data structure. So our data structure will become as follows. So our data structure, when we are going to be here, our data structure should become like this. Okay? And then we're gonna look the same thing in logarithmic time. And this is why the problem is like easy. It's nothing much, it's not too much complicated. It's just the code, maybe. So the answer will be kept in long. Why? Because it can be really big, actually. I think, do we have modulo here? No, just long is enough. So I'm going to start at the first number. And actually, what I will do is, yeah, so I will start at the first number and end on the second to last. And then I will calculate the answer. So the answer will be, so first let's calculate on the left side. On the left side, how many numbers are bigger than that number? So dp front dot upper bound on that specific number. Now the upper bound returns dp front dot. So I think why I can't do this? Or maybe I want like the distance between. So let's just put it in an iterator, and then left iterator. What was the distance between the dp front begin and the left iterator? This is the number of numbers which, so like this, the number of numbers which are smaller, are bigger than a. So no, this is actually which are smaller than a. This is the number of numbers which are smaller than a. But what I just want to do is this. I want to do this. So this tells me how many are bigger than a. And then on the left, on the right side, so on the dp back, I need to query for the, do I need to query for the upper bound or the lower bound? Let's empty. I don't want to be. I want to query for the lower bound -1. So I want to query dp back dot begin dp back dot lower bound if I -1. I think this should work. We are going to check, and the answer here is just left times right. See out answer. I think that should be fine. Oh, of course, what else we need to do is do the following: dp front dot insert a plus 1 and dp back dot erase a plus 1. So this should work. How many, like what? I'm not really sure about the distance function. Haven't used it, but it's a nice time to learn about the distance function. The distance function just takes, so 1 1, no, this is not right. So this is not -1 probably, right? Probably. So you have one number here and then two numbers here, and then here you have two numbers on the right side times one on the left side. So upper bound of this from that end. Well, this should be correct on the left. Wait, why is this correct? Insert. Oh, it's not AI plus 1, it's actually this. Yes, okay, now it's correct. So we insert this element into this set, but we pop the next element from the right set. So the right set just goes from here right now, but we insert the 10 into the left set. It passes the sample cases. Why this takes so much time? Probably because I'm streaming in the same time. It shouldn't take that much time. Whoops. So C++. So this problem should be solved, unless it's not, unless I have some bug in the code, but the first test should be fine. Why does it take so much time? Are the tests really big? What? This is logarithmic. Except the distance factor could be, is the distance linear or logarithm, or just off one time? Oh, can the distance function like be linear? Oh no, oh, the distance function is linear, so you can't use it. Okay, good to know, good to know. So what else you would do if you like can't use the distance function? Is you could find the with like, so this is to the end, so you're gonna okay, so you can't use the distance function. I had no idea that the distance function is actually linear. So I think you can do this and just, so this gives like the numbers which are smaller or equal than I, and then you need to know how many numbers are in the front set. So size on the front set, and then you will size front minus this. Okay, and this here is a little bit easier because this just dp back dot begin. Now it should work, unless it doesn't compile because this minus begin. Let's see. How was this done? Find the position. Subtract begin from the. Okay, this is one way of doing it, but on a vector. The set should be exactly the same. Let's find my family. Find my family. How did I solve this one? These were just matches. Okay. So how do I find the distance between the? Do I need to use vector? No, why would I use a vector? In linear. Why is distance even like in logarithmic form in distance? We can find what other problem used this technique. So I can do a binary search, but this is insane. Why there's no there was this minus begin. Why doesn't it work on a set though? Just what's the issue here? GCC. The issue is that there's no iterator because what is a tree iterator? Okay, it doesn't matter if it's a tree iterator or not. Does the upper well, I'm very interested what does it say in complexity about the reference here. Complexity constant for random access iterators. So it is constant for random access iterators. but is otherwise linear. Which structures do have a random access iterator? So yes, vector does have. Okay, what else has a random access iterator? Wait, what? Nothing? Only vectors? So keeping a this is kind of bad because like the solution is very well known. I just need to find the numbers which are smaller than that. Does the distance here and then logarithmic time. Segment tree won't work because of this. Maybe I had to count on that one. Set count number smaller than. But how do you find this? What distance? Wait, distance it said that. Wait, policy-based data structures? No. Wait, set doesn't. Wait, it's not well the duplicates. It's like finding a lower bound and then the distance, but distance set doesn't have a random access. Wait, the distance between how much complexity does it say this? First time n squared, because it's very, if the distance is linear time complexity, then the whole thing is quadratic. Number of elements with a key less than this, lower bound distance. Yes, but which isn't nice. It's often in iterator increments, not in application of sorting. Yes, what is a flat set? What is it? Whoa, they have data structures already written for that? This is seriously Microsoft. Of course we can do it with trees, but no one wants that. Like, you just have to know can I do it with maps? I can't somehow. Because I need to insert it in log of n time, I can't do it in a vector. I can't insert it in a vector of log of n, but I can do it in a set. So the only thing I wanted is just a random access. The only thing I wanted is the distance, like how many elements are smaller than that. But apparently you can't have that. So how do we have both without using trees? Let's see, let's investigate a little bit more. So because trees we can use, doesn't like really, it's not like binary search tree. It's unbalanced. So what about maps? Map smaller, map count smaller than x. That's says which is not only linear but also necessarily slow in practice due to non-random access. So yeah, what about multiset? Is it? It's not random access. Deque is random access. Deque is not sorted. Okay, what is this? Count if begin elements smaller than 3. Suggest count element without having to compute distance. But this is linear. Is it? You know, that's what I did. Yeah, using KVLs now. Self balancing trees, using a binary search tree. No, it doesn't like policy data structures. I've never used policy data structures, but there has now it has to be a trick because they are all distinct values. So if they're all distinct values, I can compress them down into an O of n, and then I can do a fanfic yes, what I can do is this. It's gonna be a little bit more work than like my solution, which should work, but now this distance thingy. Okay, so because there are only because there are only 100,000 numbers, I can make a fanfic tree with that 100,000 numbers, 2 fanfic trees. So okay, let's first. So I have like this fanfic tree here. Do I have this fanfic tree somewhere? Fanfic tree. Let's first create it into a structure. Let's see. Snippets. Pre-configure user snippets. Fanfic. No, there's no fanfic. Okay, let's see. Fanfic tree. Okay, this here is a fanfic tree. And it also, I have also compression here. Interesting. Wait. Oh yeah, this is okay. So let's do this. So this is compression. We'll create a new snippet. CPP call compression. This is index compression. Index compression. I really don't need this minimum element, but whatever. Okay, so now this fanfic tree we have add and get from a fanfic tree, which is fine. Let's just copy it out, and then we'll create this structure because I don't have a structure. Fanfic tree, and let's do this. So let's do this. Fanfic tree and info for the resize 0. How many elements would that be? Okay, then we can add to the fanfic tree or get from the fanfic tree. And then what we're gonna do is the following. First, we're gonna use index compression to compress all of the numbers into a smaller. Wait. Okay. To compress all of the numbers. So let's just do this comp. Should we define it all as like A? Yeah, sure, A. But no, A is the other thing. Okay. So first we insert it into a comp, we sort it, we compress it here. If A is bigger than the max element, so this is about the max element, we don't need the max. Oh, we need the max element because of the Fanfic tree. Okay, and then we're gonna create 2 Fanfic trees. This is not how we create 2 Fanfic trees. DP front, DP back. Make sure structure. This is fine, right? It's fine. And now in the DP front, it's not actually insertion into the Fanfic tree, but we're gonna add to the Fanfic tree in this position value 1 and this position value 1. And what we are going to do is we just want to get from the Fanfic tree. So size front is not actually the front.size anymore, but we want we are going to keep track of like int front size, this one, and then when we insert here front size plus plus, and here the same thing. When we insert is get Fanfic tree, but now here erasing from Fanfic tree. We just want wait, get Fanfic tree, add to Fanfic tree, and now we add to the Fanfic tree, but -1. Okay, and now we want to say this front size minus, instead of this, is dp from dot get Fanfic tree. Now get Fanfic tree we want to add to this position a of I. dp back that get Fanfic tree a of I, and this should equally work, although now we're using much more complicated data structure. Fanfic tree resize. What haven't we closed? It's bigger than the max element, but we haven't defined the max element. Okay, 0. Why is it 0? Yes, just a moment, just a moment. So, okay. Sorry for the interruption. Let's see. So now a Fanfic tree. So what happens here in the Fanfic tree? Why can't we get this? Get Fanfic tree. Okay, why is it 0? Is it always 0, or is like one of the sides 0? Here we're adding this, adding that. No, so this side works, but the left side doesn't. Front at 0 at I front. So front side is 1 minus what we get. What we get is 0. It should be 0. What we get should be 0. Let's see. Is it 0? No, it's not. It's not 0. What? Doesn't make total sense here. Wait, the numbers are like this: 4, 3, 2, 1. All right. And now we want see what is A1. Wait, what? A1 is 1. Why? What? Doesn't make sense. Let me iterate over AI to see what is happening here. Is the compression doesn't work? Oh, wait. The compression doesn't. Oh, AI here is equals to the comp I. This should work now. Yes, this works. Okay, so once again I'm going to explain why and what is going on here. Okay, so first we're index compressioning everything on every element. So instead of having like large elements, we only care what is their order. So we only care, let's say we have these, I don't know. So we only care that this is the smallest, and this is the second smallest, and this is the third, and this is the fourth. It's the same thing. It doesn't like these no more matter, okay? Because that's the same thing. The triples don't change. And then when we have this index compression, we can use Fanfic trees. These data structures are a little segment trees, which are really powerful. Let me first upload it to see if it's fine, if it passes the cases. It should now be really fast. And what Fanfic trees do, yes, it passes all the test cases very fast. So what Fanfic trees do is just so like it's a little bit harder to explain, but so like let's say we have this 4 1 3 2. Okay, now this is our only triple here. Our only triple is this, but we have two data structures, right? Two fanfic trees. One fanfic tree says that like one fanfic tree has 4 elements inside, and on the 4th element you increment that element by 1 because there's one element in that thing here. Okay, on the other side you have a fanfic tree, but then you increment the 2nd and the 3rd index. And what is really great about fanfic trees is that you can query out from the start to any position here. You can query out and the sum of these positions. So when I go here on the 3rd, so let's say I'm here on the 3rd. One of the data structures now looks like this. Now there's this. One data structures and the other data structure. So what on the one data structure is 1 0 0 1, and on the other data structure is 0 0 1 0 0. So this is fanfic tree. This is DP front. This is DP back. On one fanfic tree, I want to know which elements are higher than 3. So I query to 3, and the sum here is 1. But I know that there is one more element. I mean, I know how many elements are in this. What is the sum of all of the whole fanfic tree? I know that it's 2. So 2 minus 1 elements are bigger than 3. And this one here. So here is the result is 1. So left is 1. On the right side though, I want smaller numbers than 3. So I don't query the 3, or I query actually in my code I query the 3, but that doesn't really matter here. So I query everything which is below 3. And this here, the fanfic tree sums up in logarithmic time. Sums up, and here it says 1. So one element is smaller than 3 on this side, on the right side. So if one element is here and one element is here, the combinations, right, is 1. So it's left times right, which is 1. So one pair with 3 in the middle exists, and then we go to the next number, and so on. So it's a very, very nice problem. I like it because I don't usually use fanfic trees, but when like I see some problem like this, I really like this. However, I will create a snippet, fan tree fanfic tree. So this is a good snippet. Also, the index compression is a good snippet. These are really useful snippets. So, okay, let's go to another one. Okay, there is this very interesting problem I want to solve. It's called Rudnik. It's from the Olympiad in 2012. It's a very interesting problem. How much are we live to? No, I don't stream on Twitch now. We're live for 1 hour. We are going to do to solve one more interesting problem. Maybe what can I do is, yes, maybe we can like now translate this problem. So you have years, you have a grid of years such that each cell here represents so I'm just trying here. Yes, okay, 2015, 2012, 2013. Okay, so okay, so you have a cell. So let me just see. Like you have a grid, like some grid of cells. Each cell contains at what year is this cell going to be excavated? Like it's a little bit more complex, but let's see how we can redefine this problem. Let's, instead of years, we can write numbers. So we have some numbers, okay, in a grid. And then you're asked k queries so the grid RC, the rows, columns can go up to 300. Oh, 3, so it's like this is 3, and you have k queries. Okay, so queries q, let's say, which goes up to 10 to the 5. Okay. And you are asked if I pick, let's say, if query is 3, you're asked if I how do you say it, color the numbers which are bigger than 3. So this number is bigger than 3, this number is bigger than 3, this, 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 this. If I color all of the numbers bigger than 3, what is the number of islands formed? Which is a very fine problem, actually. What is the number of islands formed? And the solution to this problem, let's see if someone has, so the solution of this problem, so I see some people joining. The solution to this problem is very interesting, actually. Are the queries yes, the queries are sorted, so you don't have to sort the queries. Yes, they are sorted. Are they all in integer values? They are all in integer values. Okay. So my throat a little bit hurts, and that's why I don't want to talk a lot. But let's solve this problem. Let's make a new file. Let's save this file. Queries.cpp. Let's create a new problem. Let's copy this example. So, how are we going to solve this problem? This problem is very fine. Okay, because so first we want the queries, right? The queries. Let's read the queries in a vector. How do you say queries? Quiz. I don't know. So we read the queries. Now we have to read all of the how do you say it? All of the matrix. So let's query out the matrix. And RC okay, so let's read this. Okay, after reading the matrix, what we want is, if you notice out that like the years increment, so less and less of them are going to like they're going to disjoint, right? So here you have like one big how do you say island, then like here you will have two islands probably, yes, two islands. Then here you would have 1, 2, 3 islands, and here you will have 4 islands that they disjoint. But of course we're programmers and this can be solved offline. So what does that mean? For each query we're going to start from the backwards and we are going to join. So to do this I'm going to do this. Just okay. So we're going to start from the backwards, see how many islands are there, and then we join islands. This is extremely fastly done. Instead of like counting how many islands are just running BFS all the time, this is extremely fastly done with a DSU, with a disjoint set union. This is a data structure which is quite a complex one. I mean, it's not a complex data structure. It's very small data structures. That's why I like it. But it's I mean, it has its own interesting things. You have to learn it on your own. It's not actually a basic thing which I can like now explain how it works. You have to learn it really. But this is the data structure. Let me just create a snippet for this as well. Okay, so after reading this, we can put them in what kind of data structure we want to put them. I want to put them in a set. I want to create this. We want to create a structure called node. Let's say, or a cell. More better. And each cell will have the x and y coordinates, and will have the year at which is going to be excavated or something. Let me just pause the stream for a minute. Think about the solution. I will leave the problem in English right now, and think about the solution. So let's continue about our data structure. So each node will contain x and y and a year. So we can have a set here containing cells. Okay. Would it be nicer to have a vector containing cells? But the matrix should have, like, instead of this, each cell could have an ID, where in that vector it is. Each cell could have an ID. Where in that vector it is, or it could have like a neighboring IDs. Could that be also a thing here? I mean, I'm thinking about how to implement this in a way that is more understandable, rather than like in fast implementation. Maybe what I want to do is x and y ID, and then like probably I want neighboring IDs. The neighboring IDs can be get from x and y. The only thing I want is like to sort them by year. So I could have on the matrix, I could have cells here. And each cell would have the following data structure. We'll have like this is here. And then j dot xi. J, and these could be pointers to that. R times C sorted cells at R times at I times C plus at I times C plus J okay is equal to a pointer at this address. And then we want sorted cells begin, sorted cells end. And now because this sort wants an operator, I will implement an operator. What is a smaller cell? A smaller cell is a cell which has a smaller year. But do we want a smaller year or we want a bigger year? Probably want first to start from the biggest years. So I will create a DSU data structure, DSU, where is DSU? Okay, DSU data structure, DSU D. Now, and how many are there cells? R times C. R times C cells. Well, plus 1 for safety measures. Or I can't add plus 1 for safety measures because I will. So how do we know the islands? How do we know in a DSU data structure we are asked to query, oh, not using here, we are asked, oh, problem here, problem Rudnik mine. Whole stream I didn't have this. So we are asked to know that this is an island, this is an island, and this is an island, and this is an island. When we combine the threes, what we do is like this node here joins with these two nodes are in the set. So in the DSU we want to know how many we can iterate over. If we iterate 300 by 300 by this, we can't do it. So okay, so if joins in a set which is like, if it doesn't join two sets, then the set number remains. Okay. So okay. So for each query we already have the queries, right? We already have it in sorted order, if I'm not mistaken. But we are going to reverse that order. Okay, we're going to reverse that order. We reversed this order, so we're going to start from the back. And now we get year. Now we need everything which is later that year to be connected. So how do we do this? First, for the first query, we will only... No, we don't cover them. We're going to keep in every cell a boolean, is it colored? Year, an ID. What is an ID? What here we didn't say an ID. What is? This is the ID. Okay. So we're going to go through the sorted cells. Let's have a pointer. If sorted cells, add that pointer, dot. Now we want to check, is that year of that sorted cell strictly bigger than the year we're asking? If it is the case, if it is strictly bigger, we need to color that. Okay, so how do we color that? We say if we want to add the 3, we see its neighboring cells. So every neighboring cell. So here's another thing we need to do. We need this function. Okay, go through the neighboring cells. And not having this, but using K. There are 4 neighboring cells. We want to go through each of them. I already have this snippet dx dy4. Do I have this snippet d4? dx dy8 I do have. Why don't I have 4 here? Very weird. Why I don't have snippets? I should have snippets. Wait, I only have this snippet? This is not fair. Let's see, let's correct this. Well, this actually works for... wait. You're watching Upsolving on Mendo, so we're solving problems. What is the connection from left, right, up or down only? Valid. Okay. So connection from this is only valid. Okay. So this dx dy4, this is our snippet. Now for every this, so int mu x is what? Is sorted cells at that pointer dot x plus dx k. This also remains as y if nx ny are c if is valid how long? Okay, valid. Okay, if that's valid, then we can color that cell. I mean, we don't color the cell. What we do is we say that that cell and that cell are in the same DSU set. So one dsd dot merge. And now how do we merge the cells is a little bit of a problem. We're going to use probably the indexes of the cells. So what? Oh, we can't use the indices of the cells. Or we can. Yeah, we have the index of one of the cells and the index of the other cell is known. Okay, so we can use the indices. Sorted cell at pointer.id with which cell it is. It is the matrix of nx, ny, id. We merge them together. Now we have to first check are they the same. So both same set are same. So if they're on a same set, then what do we do here? If they're on the same set, or if they're on the same set, they can't be on the same set. They will never be on the same set, would they? So the whole problem is like we have merge them. So let's say this three here, this three. Now we're interested in what happens with this three here. So what happens when we add this? When let's say we're here, right? So we have to add that, right? And we look here, we look here, we look here, and we look here, right? So I have to look to all of these four corners and say the following. If there are two sets they're two not exactly same sets, but colored. So so this comes a little bit of a problem. So if it's valid, okay, it's valid. Bool, is it colored first to check? To check if it's colored, we go this and say, wait, is it colored? Okay. If it is colored, then we have to remember that you have a colored node there, right? So if colored, we add this position to probably like a set of positions. Colored adjacent nodes. To that position, we add that. Okay, and continue. Okay. we insert that. If now we go through the colored positions, if it's not colored, we don't care. If it's colored, we do care. And we go over all of the colored adjacent. Should we go all of, from like all of the colored adjacency? Yeah, probably, yeah. Color adjacency. That and okay, and now we have like multiple different islands. Like this is one island and this is another island, right? So we have to join them all with one ID, one set, and the number of sets are decreased by the colored adjacency size -1. Okay, so the color, so if there are two sets which are adjacent, but are they on the same set? So it's not colored adjacency, it's which set are they on. So for each colored adjacency, not only that we want the color adjacency, we want on which set are they on. Which set is find set on, and now here is the trick. y.id. So we find on that which set are they on, and we decrease like this the number of sets. Of course, for which with each query we are going to print out the number of sets. For now, every colored adjacency we're going to color it, of course. So auto med at first, p at second, color. We are going to color that, and not only that, we're going to color it, the set at which this goes is going, all of them are going to merge together. So all of them are going to merge together. So int id is mendo first second id int id. Now id is like merge with the now id. What is now id? Sorted cell set pointer down id with id. Okay, this is the merge, but only if this is the merge. Okay, but how do we increase a set? Well, we make it smaller but we don't increase it. Wait, we increase it, don't we? Okay, this is not right. Well, minus, this is 0, minus 1 plus 1. So, but if the year is bigger than this. Okay, and yes, of course, after this, the pointer has to go to next. So, what happens if in one query there are multiple years? So, while this pointer is bigger than this year, we're going to do this. Pointer plus plus. Okay. Wait, what's going on? I think that should be fine. I don't know what is this. See, alt ambiguous. Wait, for each year, as long as this is bigger than the year, we color it and we try to see how much is deep colored. This. And then, why are they all zeros? Okay, let's say, well, let's debug here somehow. So first year is 240. So 240, I don't see anything here. So year. So this is bigger than the year. Wait, if it's bigger than the year. What if the queries here is bigger? If here on the query is bigger than the sorted cell set pointer, while that is bigger, we want pointer plus plus. While that is bigger than this. What if they're equal? If they're equal, if they're equal, we don't care. What to do if they're equal? I will see what to do if they're equal. Oh, if this year is bigger than like everything, then can we just skip the year? If this year is bigger than everything, our year will be bigger. We can just continue. What if it's equal to this? What if I'm querying for 2013 and then they say, can I color that 2013? If sorted cells here is bigger, if it's bigger, what if it's equal? I just skip it, right? Yeah. So year is bigger, I continue, go to next year. really interested here. So 2040 continues. 2022. Is there 2022 here? Yes, there is. There are 4 with 2022, above 2022. So sorted cells is bigger than the year, yes. And then we go here. Then we go here. We iterate over all of these. We say that they're valid. Are they colored? They're not colored. We skip them. 0, minus 1, minus 1, pointer plus plus. Go. There are some equality here. Let's see. Equality. Is there some equality? We stop at the equality. We see how it sets. I don't know why it takes so much to compile. That's really weird. 2022 should get here. What is this? Yeah, this. Cell year. I don't have a second monitor to track the chat. Okay, see out ill year. Wait, what? Why is here 2013? Are they sorted differently? They might be sorted differently, actually. Is this the case? Why this doesn't work? If it's year bigger than the sorted year at the pointer 0, so the operator with the smaller sign, it gets the smaller year. Yes, that's correct. Oh, could that be the case? That we don't have an operator overshadowing for this? Could that be the case? Possibly. Or we're just gonna do a lambda expression. Yeah, I don't think the years are sorted. They are not. So why are they not sorted? Let's do a lambda expression. So const cell A const cell B turn A dot year smaller than B here. Let's see if they're now sorted. What a bunch of errors. So what is here the idea? Why can't I sort pointers? Let's Google it out. Sorting pointers. Sorting array of pointers plus. Oh, it's okay. It worked. Wait, I need a bigger here. Need the year to be bigger than that. Okay, if that worked. Okay, it worked. So cell year is to 2025. Okay, 2025. Let's see, for every cell year here, what does it happen? Okay, for cell year 2025, which size is 0, we add to the set, we print 4. So let's first see what do we print here. Do we have some? Okay, we print 4. Oh, and the results should be reversed, so we should print like answers. Q minus y minus 1 set, and then print answers. So it's 2, 3. Yes, we are correct. And why there are no prints on the last 2 years? Is that because we continue? We don't certainly want to continue. We want if this year is way bigger than any other sorted cell, we query and to print to answer q minus I minus 1 to be 0, continue. And on the last year we don't print anything, which is weird. This is weird again. This is weird. What's the idea here? Q queries q minus I minus 1. What's the matter? It is not here. That doesn't matter here. Okay. Something crashes on 2012. 2012, they're all colored. So what does that mean? Excuse me for a minute. What does that mean? Which are all covered through. So pointer goes out of bounds. Okay, if pointer is smaller than sorted cells the size and this thing here. Okay, it passed the case. So we're already a lot in the stream. We're already, what, 2 hours solving. So I'm just going to post it and see if it passes all the cases. Shouldn't be. It should pass, but probably, yeah, some wrong answers. Wrong answers probably on some edge case, some stupid edge case where you have to do some edge case work. Let's have one query which like is bigger than 4, and then have like one query bigger than 4 and have like 3 by 3. So let's say all of them are 6s. So there should be 1 on this case. But let's make, it should pass. Let's make a case where 4, so what about having like like this? Right, that was weird. There are 3 by 3 matrix. We start with 1. Oh, that was weird because we want to start with 4. Then okay. Okay, so when we start with 4, there are 5 different sets, and then with 1 there's 1. Okay, this works. What is the cases here? The cases here are big cases. It's a little bit late to debug this, but this is correct. Now let's do another configuration where let's say you have like two you have like this. First it's like out, it's like inside, and then you add outside nodes. But this is correct as well. Okay. Let me now adjust this. Let's add these here. What could go wrong? Let's examine a test case. Case 8. There was some big ass test case, but let's see. Oh, it's an enormous test case. And there are a lot of queries. So what is the difference? Let's compare this. What is the expected output? And what do I receive? So expected output is this. After this, like I know that there will be a lot of ones. After this one, so I can just plug them into like I can create two new files. Correct. And what I get. I would be very disappointed if like okay, so now let's compare them. Oh, what? I print 0? How is that possible to print 0? Print 0 somewhere. Oh, the year here. Oh, I see what I'm doing wrong. Oh, I'm seeing what I'm doing wrong. Here I'm printing 0, but what should be done here is to be printed the last possible. So here we're going to do this. So this should now pass test cases. Oh, wait, what? Wait, q minus 1. Now I need q here to be this, possibly what else? This should pass. Wait, this doesn't pass again. Wait, what is the correct? What is the wrong? What is now? Still 0? No way. No way, there's no chance to be 0. Which sets are only 4? So this here, is it correct? Maybe +1. +1, is it +1? Because we're working backwards, yeah. Okay, yes, this passes the cases. Okay. Okay, it was just that 0. Okay, and this test case is correct as well. Yes, okay. Passes all. So this for today does it. We solved two, I would say, pretty hard problems. They're both from Olympiads. And yes, that's pretty much it for today. It's been 2 hours stream. It will be probably on YouTube, but I need like to change the thumbnail, so yeah. Probably maybe then unlisted from YouTube. I don't know. It's my first stream, so I'm not really proud or anything. But there were fun problems. Now we have 150 solved here. So if you want to take a look at the problems, mendo.mk. We're gonna solve these for the next time probably. Yeah, there are interesting problems here. Very like to learn much about like different data structures, different ways of solving. Okay, thank you so much for watching, and I'll see you next time.